Okay, so we're going to look at how to define the inverse cosine of a complex number. And to get started, we'll first think about what does it actually mean to have the cosine of a complex number. So our starting point is going to be Euler's formula, the famous formula that e to the I theta is cos theta plus I times sine theta. And this formula actually holds even if theta is a complex number as well. So to get a nice formula out for cosine, we're going to substitute in negative theta in place of theta. So we get e to the negative I theta gives us cos of negative theta plus I times sine of negative theta. And then you can see on the right hand side, we know that cos of negative theta is the symmetrical function, so this is just equal to cos theta, and sine of negative theta is going to give us negative sine of theta, so this turns into a minus sine times I times sine of theta, and this is equal to e to the negative I theta. And then you can see if we take this first equation and add both sides with this last equation, we're going to get on the left-hand side e to the I theta plus e to the negative I theta gives us, we get two lots of cos theta, and then our I sine theta terms cancel. But then if we divide through by 2, we've got cos theta on its own. So this gives us a nice exponential form for cosine of theta, which we'll take as our definition now. So to actually solve this problem of what is the inverse cosine of a complex number, let's write this out and say the inverse cosine of z, let's say this is some complex number w. So what we really want then is z is cosine of w. And now we can use this exponential form with w potentially a complex number here to get that z is going to be e to the I times w plus e to the negative I times w all divided by 2. So then if we multiply through by 2, we get 2z is e to the iw plus e to the negative iw. And then we can actually turn this into almost a quadratic equation if we think about e to the iw as being our variable. So if we just multiply by e to the iw on both sides, we've got on the left-hand side 2z times e to the iw, and on the right-hand side we multiply this by itself, we get e to the iw all squared, and then when we multiply this term, the negative iw, multiply this by e to the positive iw, we just get 1, which is nice. So then when we rearrange this, we can get on the left hand side, we just get 0, subtracting 2z e to the iw. This is equal to e to the iw all squared minus 2z times e to the iw and plus 1. So you can see we've got what looks like a quadratic equation, which we should be able to solve now. And to make things a little bit nicer to work with, we can do a substitution here where we introduce a new variable. So we can say that u is defined to be e to the I times w. Then the equation becomes much nicer. You've got 0 equals u squared minus 2zu plus 1. So you can see this is just a quadratic we need to solve for u. So then solving this using the quadratic formula, we get u equals, we've got 2z, the coefficient of u, negative, plus or minus, we get the square root of this term all squared gives us a 4z squared, and then minus 4 times the coefficient here is 1 and 1 again, so just minus 4 all divided by 2. And we get some nice cancellation here as well, that 2z divided by 2 just gives us a z. And also inside this square root we've got a factor of 4, so when we square root the 4 we get a 2, and then divide by 2 we can actually just cancel out that 4. So we're going to get z plus or minus, it becomes just the square root of z squared minus 1 when we take the 4 out and divide by 2. So this is equal to u, which is, remember this is e to the iw, so we're really trying to find w here, so there's still some more work to be done. And just before we move on, I want to address, I don't think it's particularly obvious how you would take the square root of a complex number if you needed to. So here, if you imagine you've got a complex number and we put this into its polar form, so let's imagine we're trying to take the square root of r e to the I theta, where r is the modulus and theta is the argument, then it's a bit easier to see here that we just get the square root of r times then e to the I theta. The square root of this is effectively just raising it to a power of a half, so we can just divide by 2 in the power there, so it becomes e to the I times theta over 2. So this step of taking the square root of a complex number is quite natural if we put this z squared minus 1 into this polar form. And now if we're working with real numbers, the natural next step here would be to use logarithms. So remember we're trying to find w, so this would help us get w on its own. But again, we need to think really carefully about what does it actually mean to take the logarithm of a complex number. So if we have a complex number, let's say our complex number is r e to the I theta, and we want to take the logarithm of this, or the natural logarithm, what this really means is we're trying to solve the equation that this is equal to e to the power of t, and solve this to find this complex number t. So we could write this as, hopefully, t equals some sort of natural logarithm function of r e to the I theta. But again, we don't really know what to do here. So if we introduce t and write this as its real and imaginary part, so we write t equals a plus b times I, where a and b are both real numbers, then our equation that we're trying to solve becomes a bit nicer. We've got e to the a plus b times I equals r e to the I theta. And then you can see here we can split this up into e to the a times e to the b times I, and then we can read off what the modulus and argument are going to be. So we get e to the a is going to be equal to r, so this is quite nice and helps us find a, because here we can just take logarithms. We've just got a real number r, so we take natural logarithms, and a is going to be the natural logarithm of this real number r, the modulus of the complex number we're interested in. And then what about for our argument? Well, we just have e to the bi equals e to the theta times I, so a valid solution here would just be b equals theta, but this isn't the only possible solution. This isn't the only possible value of b that would also work. And this is because if you have e to the 2 pi times I, this complex number is just 1. So you could always add 2 pi to your theta or subtract 2 pi, or you could do this repeatedly. So you could also have plus, we'll write this as 2k pi, where here we've got k can just be any positive or negative integer. But how we would actually define this would be, we would use this value of theta between negative pi, and we'd call this our principal branch of the logarithm function. So let's write this out a bit more formally now. We've got t is this natural logarithm of r e to the I theta, so we're saying that our attempt at getting a natural logarithm of this complex number has given us t, which is this a plus bi, so we've got the natural logarithm of the real number r, and then we've got plus just theta times I, and here we really want theta to be between negative pi and pi. And then there's also the possibility, because this would have more than one solution, we could also add some multiple of 2 pi. But this is starting to get a bit messy, especially having to make sure that theta is between negative pi and pi. So if we actually go back to, what if we have the logarithm of just a complex number z? So we'll write this as, with a capital L, logarithm of a complex number z. We'd have, first of all, r, this is the modulus of z, so we just write this as ln of the modulus of z. This is nice and straightforward. And then theta would be the argument of z, and this works out quite nicely because the argument, by definition of a complex number, we always take this to be between negative pi and pi. So we could replace this theta by the argument of z, and then just multiply this by I. So this gives us what we call our principal branch then of the logarithm for a complex number. So we'll be able to use this now going forwards to actually solve this equation and find what w is, this inverse cosine of z. And to actually be able to calculate anything, we do need to make a choice between whether we take the positive or the negative root here. So just to begin with, we'll look at what happens with the positive root, and then later we'll look at the negative root and find all the possible solutions to this original equation. So taking the positive root there, we get on the left-hand side e to the iw, and then on the right-hand side this is just equal to z plus the square root of z squared minus 1. And then we can take this complex logarithm on both sides, so we get log of e to the iw is equal to this complex logarithm of z plus root z squared minus 1. So this is nice on the left-hand side, we just get iw, but on the right-hand side we're now taking logarithm of this, and unfortunately you'll notice that we've actually used the letter z twice here, so we're effectively substituting in z plus root z squared minus 1 in place of z in our function here. So to take the complex logarithm of this, we're going to do the natural logarithm of the modulus of our complex number, so we get natural log of the modulus of z plus the square root of z squared minus 1, and then we've also got plus I times the argument of our complex number, so plus I times the argument of this complex number z plus root z squared minus 1. So then you can see to get w on its own here, we could just divide through by I. So divide by I, that cancels, then we get ln of this all divided by I. But we can actually tidy this up a little bit, because remember that 1 over I is actually just negative I. And you can verify this if you just multiply by I on the top and bottom of this fraction. We get I divided by negative 1, so this is just negative I. So then we can read off quite a nice form then. We've got negative I times the natural logarithm of the modulus of z plus root z squared minus 1. And we've also got, now that we've got rid of this I, just plus the argument of z plus the square root of z squared minus 1. So this is our value of w. Remember w, we're defining this then, we can think of this as being like the principal branch of the inverse cosine function of z. So we can say then that the inverse cosine function of this z can be defined like this. And this is certainly one of the many values of z which would work here. But then there's lots of other possibilities as well. So we've got this plus or minus square root. So we can also have, for some alternative solutions, we can capture this by saying natural log of z plus or minus the square root of z squared minus 1. But then also for the argument, remember, we were allowed to add any multiple of 2 pi to this. So we can also have plus the argument of z plus or minus, that should be root z squared minus 1, but then we can also have plus 2k times pi, where k can be any positive or negative integer. So we can think of this first expression as being the principal branch, but then anything else of this form would also satisfy this equation if you replace this by w, so cosine of this would still get you back to having z then.